What's up, everyone? Welcome back to Math 18A College Algebra. Today we're going to be doing Chapter 4, Section 5, finishing off Chapter 4, more logarithms and exponential functions. And you know what I just realized is, after today's lecture, there's only 2 more lectures, so this semester is coming to an end like way faster than I thought it was. So without further ado, let's get into the third to last lecture. So now that we've spent the last couple sections learning about exponential and logarithmic functions, we're going to start learning how to solve expressions that involve exponentials and logarithms. So some useful properties to keep in mind for that will be one-to-one property of exponentials here. This a to the x equals a to the y if and only if x equals y. And the same for logarithms. Log base a of x equals log base a of y if and only if x equals y. So that one will be useful when solving expressions that look something like this. We also have this inverse property for like removing exponents or like bringing them down. So if we have a to the log base a of x, that just gives us x because these functions, this exponential function and this logarithmic function are inverses of each other. And likewise, log base a of a to the x equals x. So again here we use this log base a to sort of undo the a and give us just that exponent back. So let's go ahead and try our hand at some examples now. We're going to want to solve for x in each of the following expressions. So the first one we have here is 3 to the x equals 81. And so we're probably going to want to use this one-to-one property because we can see we have a to the x, a to the y sort of thing, 3 to the x, but we want to write this right-hand side as 3 to the something. So want to rewrite the right side as 3 to the something. This isn't 0, this is a circle. 3 to the something. And that's so that we're able to use the one-to-one property. So maybe we don't know what power we need to raise 3 to get to 81, but hopefully you'll remember that 81 is equal to 9 squared, right? But we also know that 9 is equal to 3 squared, so I can replace that 9 with 3 squared, and then this whole thing gets squared. Okay, I'm just replacing the 9 with a 3 squared. And then from here, we have a power raised to another power. So when we have that, we need to multiply the exponents. So we end up with 3 to the 4th on this side. So I now have 3 to the x equals 3 to the 4th. And so I can now apply the one-to-one property. And then I can see that x has to equal 4. Okay? We can now take a look at this second one, log base 6 of x equals 3. So here, it looks like we're going to want to use the inverse property. We have a log base a of x, essentially, and we want to solve for x. So looking at this inverse property here, this a to the log base a of x, we're going to want to raise both sides of this equation. Or not raise, but like exponentiate is what it's called. So I'll show you over here. We're going to make a base 6 for both sides, and my old equation becomes the powers of this 6. So basically what you're doing is just like taking a 6 base on both sides, and then, like I said, this old equation becomes our exponents. And so using the inverse property now, you can see that this a to the log base a of x just equals x. We have 6 to the log base 6 of x, so this left-hand side now becomes just x. And the right-hand side is 6 cubed, which you can throw in your calculator, or 6 times 6 times 6, that's 36 times 6 is 216. So x equals 216. All right, finally for the last one here, natural log base 5 minus natural log of x equals 0. So it's not quite in the form that we want it, which might be concerning, but we can easily rewrite this. We can add this natural log of x to both sides. So let's go ahead and do that first. Plus natural log of x. So I'll now have natural log of 5 equals natural log of x, because we cancel on this side. So again, we can apply the one-to-one property again, because log base a of x equals log base a of y if and only if x equals y. And remember that natural log is just log base e. So we can see that these arguments, this 5 and this x, have to be the same by the one-to-one property. So here x equals 5. Alrighty, so I looked through the rest of the chapter, and it's actually just a lot of examples of solving these exponential and logarithmic equations. So the video will just continue to do examples, and they'll get progressively harder throughout the video. So let's go ahead and take a look at this one. Solve for x and round to 3 decimal places. So we have 6 to the x equals 84. Alright, and so the last time we had something like this, we tried to rewrite the right-hand side to be a power of 6, or whatever our base was. But here, 84 is not a power of 6. So we can't do the same thing. So instead here, we're just going to want to take log base 6 of both sides. So that'll be our next step. Take log base 6 of both sides. And remember, that's just because that's the inverse property. So by taking log base 6, we can essentially undo this power on the left-hand side. So let's go ahead and do that. Log base 6 of 6 to the x equals log base 6 of 84. So this left-hand side is going to just give us back x, because log base 6 undoes the 6 to the x. And then the right-hand side, we can't use our calculator to solve this quite yet, because most calculators don't have a log base 6 button. They just have log 10 or natural log. So we're going to have to use the change of base formula now. Use change of base so that we can plug it into our calculator. So let's go ahead and do that over here. Log base 6 of 84 equals log, we'll go to log base 10 for this one, and we can do natural log on a different example. So log base 10 of this 84 over log base 10 of 6. And that's just applying the change of base formula directly, which we went over in the last video, or you can look it up in your textbook. So we now have that x equals log base 10 of 84 over log base 10 of 6. So now we can plug this into our calculator, and we're going to round to 3 decimal places. So let's go ahead and try that. Using the log button, that gives me log base 10, plug in 84, and then divide by log base 10 of 6. Alright, so I'm getting 2.47, and then we're going to round here. It's 2.8, so this 2 is going to round up to a 3. Alright, now we want to solve e to the x plus 5 equals 60. So we're going to want to isolate that e to the x. Let's do that first. Isolate e to the x. So to do that, I will take this 5 to the other side, and I'm left with e to the x equals 55. Then, in order to undo e to the x, I need to take natural log of both sides. because remember, natural log is log base e, and we want to take that x down from this power, so we need to take log base e of both sides, which is natural log. So let's go ahead and do that. Natural log of, that turned out ugly, natural log of e to the x equals natural log of 55. And so the natural log and the e are going to cancel out, right? The natural log undoes the e, leaving me with x on the left-hand side. And the natural log of 55 I can just plug into my calculator. So let's go ahead and do that. Natural log of 55. And we're rounding to 3 decimals again, so that's going to give me 4.0007. 007, huh? Alright, let's go ahead and try this last example here. 3 times 2 to the x equals 42. So again, we're going to want to isolate our exponent here. So isolate the 2 to the x in this case. And so we're going to want to divide both sides by 3 to get this 3 to cancel out here. So then we have 2 to the x equals 42 divided by 3, that's 14, I believe. Yeah, looks right. And so again, we can't write 14 as a power of 2. So that means that we're going to want to take log base 2 of both sides. So let me go ahead and write that. We'll annotate take log base 2 of both sides. Alright, let's go ahead and go to a new slide. Log base 2 of 2 to the x equals log base 2 of 14. Sorry, my dog's barking. I don't know what's happening. Okay. And so remember, we're using the inverse property again. This log base 2 of 2 to the x gives us back x because it undoes the exponent there. But here, again, we can't plug this into our calculator. So again, we need to use the change of base formula. So I'll do that on the side here. Log base 2 of 14 equals, why don't we take it into natural logs this time? Natural log of 14 over natural log of 2. Alright, so that's what we have on the right hand side. X equals natural log of 14 over natural log of 2. And we have a natural log button on our calculator, so we can go ahead and plug that in. So let's do that. Natural log of 14 divided by natural log of 2. And remember to always round at the very end, if you can, to get the most accurate answer. So then this equals 3.807, rounded to 3 decimals. Alright, let's now do some examples on solving logarithmic expressions. Natural log of x minus 4 equals 0. So in order to get rid of this natural log, we're going to want to exponentiate on both sides. So I'll call it exponentiate with base e, because natural log is log base e, so we're going to want to take e to the power on both sides. And then this left-hand side, the e and the natural log cancel out, essentially. They undo each other. So we're left with x minus 4 here. You take the whole argument. And then on the right-hand side, e to the 0 is just 1. Because remember, anything to the 0th power is just 1. So we're left with this linear expression that we just need to solve for x. So to do that, we will add the 4 to both sides and find that x equals 5. Alright, let's go ahead and try the next one. Log base 3 of 2x equals 4. So again, we will exponentiate. This time we'll take base 3 . So 3 to the power, this whole thing, 3 to the power of 4. And that will undo our log. So we have 2x, you take the whole argument. And then on the right-hand side, we have 3 to the 4th. So we're going to want to figure out what that 3 to the 4th is. So I'll do a side calculation over here. Maybe I'll go in red. 3 to the 4th equals, well, we actually did that earlier, didn't we? So you can think of this like 3 squared, right? Because we know that when you have a power to a power, you have to multiply the exponents. So this is going to be 9 squared, which is 81. So if you don't know it, you can figure it out, or you can plug it into your calculator. Either way will be fine. So we now have 2 to the x equals 81. Lastly, we need to divide by 2. And we'll just end up with x equals 81 over 2. And this is how you could leave your answer. This would be perfectly acceptable. Okay, let's go ahead and try a slightly harder example of a logarithmic expression where we want to solve for x. So you see here that we have 2 log terms. They have the same base, fortunately, so that's nice, but we don't really know how to deal with this in this form. So the first thing that we're going to have to do is condense. Condense this sort of expanded expression into a single logarithm, into a single log. And not the 2, of course, on the right-hand side, just the left-hand side. So remember that, let's use a different color, log of uv equals log u plus log v. So here we have sort of a log u plus log v situation. So we can rewrite this as a product. Log base 6 of, here we have, this is our u, this is our v. So we have x times x plus 5. And the right-hand side will stay the same. Alright, now we should simplify a bit. Simplify the argument that we have there within the log argument. So all we have to do is distribute that x into this factor, this x plus 5 factor here. So x squared plus 5x. And again, the right-hand side will stay the same. Okay, so now we know how to solve this. We want to exponentiate. Using base 6. Right, we always have to match the base of the log. So let's take 6 to the power on both sides. So we now have 6 to the power log base 6 of that argument, and 6 squared on the other side. So the 6 and the log 6 are going to undo each other. So we have x squared plus 5 on the left side. And now we have 6 squared on the right-hand side, so that's going to be 36. Alright, quadratic. So let's write this quadratic in general form, like we've seen so many times in the past. X squared plus 5x minus 36 equals 0. And so, as you know, I like to factor. I think it's faster, but if you don't know how to do that, go ahead and use the quadratic formula. But let's think of factors of negative 36 that sum to positive 5. And so you want to be thinking 9 times 4 is 36. Let's scooch this over a little bit. So 9 and 4 of some form are going to work, but I'm going to want negative 4 here because I want to sum to positive 5. And that will multiply to negative 36. So then this factored looks like x plus 9 and x minus 4 equals 0. So remember, in my directions it says to solve for x, so we're going to want to take this a step further. So we had x plus 9, x minus 4 equals 0. X equals, splitting these up like we always used to, x equals negative 9, and x equals 4. Now, there is something that matters here that we need to check, and that is extraneous solutions, which we haven't done in a while. But remember, we don't have the domain of all real numbers for logarithms. We can only plug in positive numbers. So let's go back to our original expression here. We have log base 6 of x and log base 6 of x plus 5. So let me go ahead and copy that real quick. Log base 6 of x, log base 6 of x plus 5 equals 2 is what it was, right? Yes. Okay, so I want to look at these arguments, and I need these to be positive. I need these to be greater than 0. So you'll notice that if I plug in the positive 4, we're fine in both cases, right? Because I'll have log base 6 of 4, log base 6 of 4 plus 5 is 9, so those are fine. But if I plug in that negative 9, I'm going to end up with log base 6 of a negative number. So, can't take log of a negative number. So that means that this negative 9 is actually extraneous. So the only solution here is going to be that x equals 4. Alright, and then we'll quickly do a final example from one of the past final exams, and that'll be the last thing that I do for you guys today. So let's go ahead and read this. Damien is saving money for college and currently has $57,000 saved. He puts this money in an interest-bearing account whose balance t years from now will be p of t equals 57,000 times e to the 0.06 t dollars. How many years will it take Damien to reach his savings goal of 120,000? Alright, so word problem, but we don't have to piece together the equation or anything. We're given this equation here, we just have to figure out how to use it. So, what are we looking for? What do we want to find? Well, we want to find how many years, right? So that means we're going to be solving for t. What else do we know? We know that his goal is that 120,000. And so we're going to have to put that in this equation, and we're going to put it in for the p of t, because p of t gives us the balance after t years. So we want to figure out what value of t is going to give us this balance here. So let me go to a new page, and we'll set that up. So 120,000 equals 57,000 e to the 0.06 t, right? Double check, yes, okay. Alright, so we're going to want to solve this equation for t. So first thing that we'll want to do is isolate the, exponent, or exponential part. So here that's going to be that e to the 0.06t. So that means the first thing that I have to do is divide this whole equation by 57,000. So divide on both sides. Cancels on this side. Let's see what 120,000 divided by 57,000 works out to be. So 120,000 divided by 57,000. Alright, and it's not actually a very nice number, so you can leave it like this for now, because remember, we always want to round at the end. So, yeah, I would probably just leave it like this for the time being. And then we have e to the 0.06t on the right-hand side now. So, we want to bring this power down, which means we need to cancel out that e. So to get rid of the e, we need to take natural log of both sides of our equation. And so we'll end up with natural log of 120,000 over 57,000 equals ln of this e to the 0.06 t. So then the left-hand side, we'll just keep it like that, write it the same way. But on the right-hand side, the natural log and the e are going to undo each other, and we'll be left with this argument on the e. So 0.06t. So then the last thing that I have to do to solve for t would be to divide by the 0.06 on both sides, as we always do. So divide this, cancels here. This whole thing is going to be over 0.06. And so at this point, this is where you're going to want to plug this whole expression into your calculator. So we'll evaluate the natural log of that fraction. So I would actually start with the fraction. 120,000 divided by 57,000. And take natural log of that. I guess it sort of depends on what kind of calculator you have, but you could also just do natural log of 120,000 divided by 57,000, like within the parentheses. So yeah, just make sure you're careful about it, parentheses where you need them so you get the right answer. And then once we have that answer, we'll divide this by 0.06. And so that's going to give me t, I'll go back to black, t equals 12.407. And I don't know if it told us to round, but yeah, I'll just take it to 3 decimals for now. So that's going to be 12.407 years. Or if it wants you to round to the nearest year, then you would just say, like, about 12 years. But, I don't know. Be careful when you're reading the directions, because, like, it'll either tell you or, like, you can ask about it, and, yeah, we'll tell you what to do for that. Okay, so, yeah, that was the last example that I wanted to do today. Another kind of short lecture, but the section was pretty short, and then, like I mentioned at the beginning, we only have 2 sections left, so thanks for sticking with me, guys. See you next week.